Today we're going to be talking about how to find the arc length of a vector function, and in this particular problem we've been given the vector function r of t is equal to the square root of 2t times I plus e to the t times j plus e to the negative t times k, and we've been told that t is defined on the closed interval 0 to 1. Now the formula we're going to be using to find arc length of the vector function is the formula I've written here for L, and it's adapted from the arc length formula that we use for parametric equations. And the reason that we've adapted it from parametric equations is because, of course, when we're dealing with a vector function, we can essentially break this vector function down into parametric equations. We take the coefficients here on I, j, and k and turn them into parametric equations. So what we're going to do is we're going to say that x is equal to the square root of 2 times t, because we're just taking the coefficient here on I and defining it as the first part of our parametric equation, so we set that equal to x. Then we're going to say y is equal to the coefficient on our j term here, so we're going to get e to the t. Then we take the coefficient on k and we say that z is equal to e to the negative t, and now you can see that we have a set of parametric equations. Now remember that when we had parametric equations before and we were looking to find arc length of the parametric equation, as long as they were continuous, our formula looked exactly like this one, except that we had left out this dz over dt squared term. Everything else was exactly the same. So it's really very similar, and all we're going to do, of course, is find the derivatives of each one of our parametric equations and then plug them into our arc length formula. So dx over dt is going to be the derivative of our x equation with respect to t. So if we look at that here first, we're going to say dx over dt, taking the derivative of both sides. Now the derivative of square root of 2 times t is just going to be square root of 2. The t will drop away. Taking the derivative of y with respect to t, we'll get dy over dt is going to be equal to, of course, e to the t just stays the same, so we'll leave that. And then taking the derivative of z, we'll get dz over dt is going to be equal to, now here we have to bring this negative 1 coefficient on the t here. We have to bring that down in front of the e, and we're going to get negative e to the negative t for the derivative. So now we have all three of our derivatives. We can plug those into our arc length formula. For a and b, we have this defined interval, this closed interval from 0 to 1. So we're going to plug in 0 for a and 1 for b. So we're going to say that our arc length is going to be equal to the integral from 0 to 1 of the square root, and now here we just plug in our components. So we have dx dt is equal to the square root of 2. So we'll say square root of 2, and of course according to our formula, we have to square that. We see that right here. Now we're going to add to that the square of dy over dt, and we know that dy over dt is e to the t, so we'll say e to the t squared, and then add in here negative e to the negative t squared for dz over dt squared, and of course we have our dt here out on the end outside of our square root sign. So when we simplify this, our goal is going to be to simplify what's underneath our square root sign so that we can take the square root easily and drastically simplify this integral. So simplifying what we have under our square root, the square root of 2 squared, of course, is just going to give us 2. E to the t squared will give us e to the 2t. And remember, that's because of our exponent rule. When we have x to the a and we raise that whole thing to the power b, we get x to the a times b to the ab. We multiply those exponents together. So multiplying t and 2 together, we get 2t. So we're going to say plus e to the 2t. Same thing here, we have e to the negative t. This negative sign in front here before we go further. When we square that, that's going to go away, obviously, so this is just going to become a positive sign. We can ignore that. Then we have e to the negative t squared. So when we say negative t times 2, we get negative 2t. So we say plus e to the negative 2t. And again, this negative sign drops away because when we square it, it becomes a positive sign, and we see that positive sign right there. So here's our square root, and then we have dt. Now, how are we going to simplify this? Well, this is a little bit tricky. Sometimes you can factor what's underneath your square root sign into a perfect square, and then it's easy to take the square root. Sometimes if you have trigonometric identities here inside of your arc length formula, you might end up with sine squared of x plus cosine squared of x, for example, in which case if you can isolate that identity, you can substitute 1 for that because sine squared of x plus cosine squared of x is equal to 1. So if you have that, you can cancel it out. We're just looking to simplify what's underneath this square root sign in some way. This one is a little difficult because even though it may not look like it right away, we can actually factor this value. What we're going to get is L is equal to the integral from 0 to 1. Here we'll have our square root sign, and underneath our square root sign, we're going to get e to the t plus e to the negative t squared, and that's going to be underneath our square root, and then we'll get dt. And if we FOIL this back out, what we see is that we're going to end up with this, and let's do that really quick just to prove it to ourselves. So e to the t plus e to the negative t times e to the t plus e to the negative t. If we multiply these together here, we'll get e to the t times e to the t. That's going to give us e to the 2t, because remember that's the exponent rule. X to the a times x to the b is going to give us x to the a plus b. And when we have t plus t, we get 2t. So e to the 2t. When we multiply e to the t here, the first term, by e to the negative t, the last term, we get t plus a negative t, or t minus t. That becomes 0. So we get plus e to the 0. Same thing here with our inside components, e to the negative t times e to the t. We'll get e to the 0 plus e to the 0. And then our last components here, e to the negative t times e to the negative t, adding those together, we get plus e to the negative 2t. And as you can see, we have here e to the 2t plus e to the negative 2t. And then this becomes here 1. And this becomes 1 because anything raised to the power of 0 is 1. 1 plus 1, we get 2. And now you can see that this value here is the same as what we had under our square root sign. So that's how we know we did the factoring correctly. So that one's a little bit difficult to see, but you always want to try to factor if you can. Because now we have this perfect square, and when we take the square root of a perfect square, those things cancel. We're left with L is equal to the integral from 0 to 1 of e to the t plus e to the negative t dt. Now, of course, we can go ahead and take our integral because both of these terms are easy to integrate. What we're going to get when we take the integral of e to the t is just e to the t. When we take the integral of e to the negative t, we keep it the same, e to the negative t. This is chain rule here. We keep it the same, but then we have to divide by the derivative of the inside function. With the inside function is negative t, and the derivative of negative t is just negative 1. So dividing this term here by negative 1, we just end up with a minus sign in front. So e to the t minus e to the negative t, we evaluate that on the interval 0 to 1. So what we're going to get here is just that the length is equal to, we're going to plug in our upper limit of integration here first, 1. So we're going to get e to the 1 minus e to the negative 1. Then we'll subtract whatever we get when we plug in 0. So e to the 0 minus e to the negative 0, but negative 0 we don't need to write, we can just write 0. So there we go. E to the 0 minus e to the 0, obviously those are going to cancel, so we don't need to look at them. We're just going to get L is equal to e to the first power, so just e, minus e to the negative 1. So we can leave our answer like this, but remember, if you're taking like a multiple choice test and you don't see this answer as one of your options, remember that this is the same thing as e minus 1 over e. We can get rid of this negative 1 exponent by moving it to the denominator, so e minus 1 over e is the same thing. We could combine these into one fraction to try to simplify further if we wanted to, multiplying this first term here by e over e, so we get e times e over e minus 1 over e to find a common denominator. And what we're going to get there is e squared here over e. So we'll say equals e squared over e minus 1 over e. And when we combine those fractions, because now we have a common denominator, we get e squared minus 1 over e. So what we see is that this answer is the same as this answer, which is also the same as this answer here. So you might see it written in several different ways. You just want to be careful about making sure that you pick the right answer if you're presented with answer choices like these. But that's it. That's how you find the arc length of a vector function.